Hello students, welcome to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now today we are going to discuss very important and very basic concept for engineering static students, which is the rectangular components, or you guys can say that how to represent a given vector, or we can say how to represent a given force in terms of its components, or we can say that how to write a given vector in its components form. So as we know that we can add more than two vectors, or we can add two vectors, or we can add more than two vectors by head to tail rule, but we can also split a given vector into two or more components. So when we split a given force into at least two components, so and if those components are perpendicular to each other, then those components are known as rectangular components. We can split a given vector into any number of components, but if we split a given vector into two components, and if these two components are perpendicular to each other, then we say that these components are rectangular components. So let's say if we are given this force F, and if you want to split this force F into two components which are orthogonal to each other, which are making 90-degree angle with each other, so then what we do is that we drop a perpendicular from the head of a given vector onto two set of axes. So normally we want to represent this force F in terms of two rectangular components, one along the x-axis and one along the y-axis. Since if we want to represent a given force into two components, then we are dealing with a force which is acting in a 2D plane, which is acting in the x and y plane, just like this screen or writing board, so which has two dimensions, the x and y. So now this force F is acting in a 2D plane, or we can say this force F is acting in the xy plane. So if you want to split this force F into two components, one along the x and one along the y, what we do is that we drop a perpendicular, we drop a line from the head of this force F onto this x-axis, and that line should be making 90-degree angle with this given axis. So wherever this perpendicular intersect with the x-axis, what we do is that we draw a vector from the tail of this force F to that intersection point. And what we say, if this perpendicular is dropped on the x-axis, if it intersects with the x-axis, then that component, or that vector which is acting along the x-axis, is known as the fx component. Since this component, we can say that this is the child of this force F, which is acting along the x-axis, and that's why we call it f of x. And similarly, if we drop another perpendicular from the head of this force F onto the y-axis like this, and again this line should be perpendicular, and if we draw a force, if we draw a vector from the tail of this given force to the point of intersection somewhere here, so this component, or we can say this vector which is acting along the y-axis, is the component of this force F, and that component is known as f of y. And similarly, if we add both of these components, they must give us that force F by head to tail rule. If somehow in a problem or in a case, if we are given f of x and f of y, so the sum of f of x and f of y must give us that force F. So if we complete the parallelogram, if I draw f of x, and then if I draw f of y here, if I join f of y, if I join the tail of f of y with the head of f of x, so then this means that we are adding f of x and f of y by using the head to tail rule. So if we add f of x with f of y by head to tail rule, then we must obtain that force F, which is the parent of f of x and f of y. So we can say that the force F will be equal to f of x plus f of y. And as we know that the unit vector which is associated with the x-axis is I hat or I cap, and the unit vector which is associated with the y-axis is, we know that this is j cap. So sometimes we are asked to write a given force F in terms of the I and j unit vectors. We can say that force F can also be written as Fx I plus Fyj. So if this f of x component is acting along the positive x, then we say that this is positive f of xi. This f of x is acting in the positive x direction, which means that this f of x is acting in the positive I direction. And similarly, if this f of y is acting in the positive y direction, we say that this f of y is acting in the positive j direction. If, let's say, if this force F was acting somewhat like this, if let's say if this was our positive x-axis and if this was our positive y-axis, and the force was, let's say, acting like this, this was that given force F and it is making some angle theta with the x-axis, then if we drop a perpendicular from the head of this force F, we will have the f of x component in the positive x direction, and we will have f of y in the negative y direction. So then in that case, if this is f of x and this is f of y, in that case we say that this force F is equal to, now the x component is in the positive x, so we say that this is plus f of x I and f of y is in the negative y, so either this is minus, since this f of y is now acting in the negative j direction. So this is the negative j direction. So we say plus f of x I minus f of y j. So the plus minus tells us the direction of the arrow where it is heading. So if the component is acting in the negative y direction, we must write minus j. And if the component is acting in the negative x, we must write minus f of x I. So this is how we can represent, we can split a given force into two components, and if these two components are making 90 degrees with each other, then these components are known as rectangular components. And we can represent that force F in terms of the rectangular components as a Cartesian vector. While we write it as I and j components, we always say this is f of x I plus f of y j. And if you want to find the magnitude of this force F, we say that the magnitude of that force F, we can always use the Pythagoras theorem. Using this right angle triangle, we can say that the magnitude of this force F will be equal to f of x square plus f of y square under the square root. This will always give us the magnitude of this force F if we are given the magnitude of f of x and the magnitude of f of y. Now if I write this force F, if I say that this force F is equal to f of x I plus f of y j, and now we are given that this force F is making some angle theta. So we know these trigonometric ratios, so which is sine of opposite divided by hypotenuse, cos of adjacent divided by hypotenuse, and so if we apply this cos of adjacent divided by hypotenuse, if I say that cos of theta, if we use this right angle triangle, so cos of theta will be equal to this base or this adjacent side, which is f of x, divided by the hypotenuse, which is this force F. So we can say that for this angle theta, f of x is equal to f cos of theta. And similarly, if we apply this, the sine of the angle is equal to the opposite. So the opposite is f of y divided by the hypotenuse, which is the force magnitude. So we can say that f of y magnitude is equal to f sine of theta. And again, if I put these magnitudes in this equation, we can say that f vector, f vector is equal to f cos of theta in the positive I plus f sine of theta in the positive j. But remember, this is very important, remember that this f of x is not always, the magnitude of this f of x is not always equal to f cos of theta. This is very important. This maybe this f of x may be equal to f cos of f sine of theta. And similarly, this is not the thumb rule that f of y must always be equal to f sine of theta. So the magnitudes of f of x and f of y all depends on the location of the angle, whether the angle of the force is given with f of x or if the angle of the force is given with f of y. Let's say if we are given angle alpha here, so then for the angle alpha, f of y will be the cos component. So the thumb rule is always remember that the component with which the angle is made is always the cos component. The component with which the angle is made is always the cos component. So this is the thumb rule. Now if we are talking about the angle theta, so for angle theta, f of x is, you guys can see that the angle is made with the x-axis and f of x is acting along the x-axis. So in other words, we can say that the angle is made with the f of x. So if a given force is making an angle with a x-axis, then f of x is the cos component, remember. So then for this theta, then this f of x is f cos of theta. And for this angle theta, f of y is, if f of x is f cos of theta, then obviously f of y will be the f of sine of theta, right? So we can say this is f sine theta. But now if we are given the angle with the along the y-axis, or we can say if we are given the angle with the f of y component, let's say if we are given the angle with f of y, let's say this angle, then for angle alpha, f of y is the cos component. So we can say that for angle alpha, then f of y is the cos component. So we can say that according to angle alpha, since this force f is now making angle alpha with f of y, so we can say that f of y will be f, this will be f cos of alpha. And now f of x is the sine component, but with respect to the angle alpha. So again, the thumb rule is the component with which the angle is made is always the cos component, and the other component will be the sine component. So now if this is the case, if you want to write the force f in terms of theta, then this will be the Cartesian vector representation. And similarly, we can write in terms of alpha, we can say that this force f is equal to, we can say this will be equal to f sine of phi according to that angle alpha. So this will be f sine of alpha I plus f cos of alpha j. Now sometimes in engineering statics we are given a force f, or we are given a vector in 3D, in 3 dimensions, that is along the x, y and z, and we are asked to find the components of this force f or this vector A along the x, y and z axis. In case of 3D, we have 3 components since we have x, y and z axis. So now the idea will remain the same. What we will do is that we will project a perpendicular from the head of A onto the z axis, and we will project a line onto the xy plane, right? This is the xy plane. On the floor, we have to project one another perpendicular line onto the floor. So this will be the perpendicular, right? And this is the perpendicular. So now if we observe this given vector A from this direction, so we will be able to see the vector like this. This will be that vector A. If we look from this direction, the z-axis is in the upward direction, so this will be our z-axis. This will be our z-axis, and this vector is along this line. Let's say that the origin is represented by O. So this will be like this, right? So this line is, we are looking to this whole plane from this particular direction, right? So we have, if we drop a perpendicular onto the z-axis, so we will have one component along the z-axis, and this component will be f of z. And since this line is in the xy plane, so we will have one component, let's say if we are representing this by a vector, so then this will be, we can say this will be az, and this will be the component of a in the xy plane. And if this is that a vector, then we can write the magnitude of, or we can say, we can write this a vector in terms of az and axy. So we can say that this a vector will be equal to az plus axy. If we add this is axy. If we add az and axy by head to tail rule, this is az. So they will give us this a vector, since both of these components are perpendicular to each other. So these az and xy are the rectangular components of this a vector. And similarly, then if we look from the top, then we will be able to see the projection of this a vector on the xy plane. And from the top, we will be able to see the y-axis and the x-axis. So from the top, we will be able to see the y-axis, and we will be able to see the x-axis. And the axy component will be visible like this. And now to write this axy into two further components, what we need to do is that we need to project again two perpendicular lines from the head of this axy onto the y and x-axis respectively. And if I draw a vector from the tail of this axy onto the point of intersection, similarly we can draw another vector like this. So now, as you guys can see, this vector, which is the component of this, is acting along the x-axis. So we can say that this is ax, and similarly this vector, which is the component of this axy, is acting along the y. So this is ay. Similarly, we can say that axy vector is equal to ax plus ay. So now let's say if we substitute this into this equation, we can say that a vector, initially that a vector was equal to az plus axy, or we can say that this is equal to axy vector plus az vector. And now if I substitute this axy here, then we can say that a vector is equal to ax component, ay component or vector plus az component. So in 2D there was only two components, so we used to write a, or the force F, equals to fx plus f of y, and in 3D there is one another component, so ax plus ay plus AZ. And similarly, if we say that if the AX component is acting in the positive x, this means that this is acting in the positive I direction. So we can say that this is the positive I, this is the positive j, and this is the positive z, or we can say this is the positive k. So if you want to represent this A vector in terms of its I, j, and k Cartesian unit vectors, we can say that this A vector, is equal to AXI plus AYJ plus AZK. And similarly, applying the same Pythagoras theorem, we can find the magnitude of this A vector. So we can say that the magnitude of A vector will be equal to AX square plus AY square plus AZ square. So this is how we can represent a given vector in 3D in terms of its three components, AXI plus AYJ plus AZK. And we can find the magnitude by taking the sum of the squares and then taking the square root, always using the Pythagoras theorem. Now there is one another important concept which the students always confuse themselves, which is very easy. If you followed the whole lesson with me, then in the start I have told you guys that the component with which the angle is made is always the cos component. So sometimes we are given the angles of a given vector with x, y, and z axis respectively. The orientation of a given force or the orientation of a given vector is given in terms of three angles, and those three angles are made with the corresponding axes, or we can say that we are given the angle with the x-axis, with the y-axis, and with the z-axis, and those angles are known as coordinate direction angles. So now we are going to discuss the coordinate direction angles. So we are given a vector A which is acting along a unit vector UA, and we are given the angle of this vector A with the x-axis, which is angle alpha, with the y-axis, which is angle beta, and with the z-axis, which is angle gamma. So now if we look into this diagram, and if we look into the blue triangle, if I drop a perpendicular from the head of this A vector onto the x-axis, if I draw a line which makes 90 degrees with the x-axis, and if we observe that triangle, which is the blue triangle, if we observe that blue triangle from here, then we will be able to see a right angle triangle. This line, which if we join this corner with this corner, are the diagonal which joins the corners of this face, which is facing towards us, is the perpendicular. Or we can say that the opposite side of a right angle triangle, AX is the adjacent side, and this A vector will be the hypotenuse. If we look into this blue triangle, then angle alpha is made with AX. So as I have told you people in the start, that the component with which the angle is made is always the cos component. So now if we don't look into this triangle, and if we know that concept, that the component with which the angle is made is always the cos component, and if we know that alpha, beta, and gamma, these are the angles of a given vector with x, y, and z axis respectively, then we can close our eyes and we can say that AX is the cos component in terms of the angle which is given with that component, which in this case is alpha. So we can say that AX is A cos of alpha, AY is A cos of beta, and AZ is A cos of gamma. So never confuse yourself with this diagram. So whenever we are given the coordinate direction angles, which are the angles of a given vector with corresponding axis, with x, y, and z axis respectively, then whichever angle is given with the x-axis, a x component will be the cos component according to that angle. So now we can say that if we are given alpha angle with the x-axis, beta angle with the y-axis, and gamma angle with the z-axis, we can close our eyes and we can say that ax is a cos of alpha, ay is a cos of beta, and az is a cos of gamma. So now you guys can say that ax, ay, and az all are cos components according to their corresponding coordinate direction angles. So whichever name is given to the angles with x, y, and z axis, ax, ay, and az will be the cos components according to that given angles. So if the angle is, let's say, angle x, angle y, and angle z, then ax will be a cos of x, a cos of y, a cos of z. Or let's say if we are given x1, let's say if the angles are given is in terms of in place of alpha, beta, and gamma, let's say if we are given angle p, angle q, and angle r, then we will say that ax is a cos of angle p, ay is a cos of angle q, and az is a cos of angle gamma. So whichever angles are given, ax, ay, and az will be the cos component, since the angles which are given are already made with those particular components. So again, the thumb rule is the component with which the angle is made is always the cos component. So now if we know that for angle alpha, beta, and gamma, which are the coordinate direction angles, ax is a cos of alpha, ay is a cos of beta, and az is a cos of gamma, and we know that we can write this given vector a equal to axi plus ayj plus azk. So now we know that a vector is equal, now ax is a cos of alpha, ay is a cos of beta, and az is a cos of gamma into k. And similarly, if I take this a common, so we can say that this is equal to a magnitude multiplied by cos of alpha I, cos of beta j, and cos of gamma k. And we know that we can always write a given vector. Vector a will always be equal to its magnitude. So this a is the magnitude of this vector, a magnitude times the unit vector. And we can say that the unit vector for given vector a. So this means that whatever written in this brackets is the unit vector. So if in any engineering statics problem, if we are given a unit vector, we can always find this alpha, beta, and gamma angles with the x, y, and z axis respectively. We can always find, if we are given a unit vector, we can always find alpha, beta, and gamma. And we can say that the components of a unit vector are cos alpha, cos beta, cos gamma. So from this we can say, from this comparison we can say that unit vector along this vector a will always be equal to cos of alpha, cos of beta j, and cos of gamma k. And as we know that the magnitude of the unit vector is always equal to 1. The unit vector always tells us only the direction. Its magnitude is always equal to 1. So this means that if we find the magnitude of this unit vector, this must be equal to 1. So again, using the Pythagoras theorem, we can find the magnitude of a unit vector by taking the sum of the squares of these components and then taking the square root. So we can say that the magnitude of this unit vector A will be equal to cos of alpha square plus cos of beta square plus cos of gamma square, then taking the square root. This will always be equal to 1. So we can say that cos square alpha plus cos beta square cos of gamma square under the square root is equal to 1. If I erase this, and if I take square on both sides of equation, if I write it like this, if I take square on both sides of equation, we can say that cos square alpha plus cos square beta plus cos square gamma, this is equal to 1. So if we are given a unit vector, so the components of the unit vector will always be cos alpha, cos beta, cos gamma. And if in a given problem, if we are given alpha and beta angle, and if we are not given gamma angle, so using this equation we can always find the third angle. So to summarize this topic, if we are given the coordinate direction angles, which are alpha, beta and gamma, so ax, ay and az will be cos components for those alpha, beta and gamma. So x will be a cos of alpha, ay will be a cos of beta, and az will be a cos of gamma. And this cos of alpha, cos of beta and cos of gamma, these are the components of the unit vector. Let's say if this is our a vector, which is equal to axi plus ayj plus azk, and if we write it is, since ax is a cos of alpha I plus a cos of beta j, a cos of gamma k. And we also know that this a vector is equal to a magnitude times the unit vector along that given vector a. So now we can say that this unit vector, we can say that this unit vector a will be equal to a vector divided by a magnitude. And we know that a vector is this axi plus ayj, so we can write it like this. This is axi plus ayj plus azk divided by this magnitude. Or we can say, in other words, we can say that this unit vector a will be equal to ax divided by a I plus ay divided by a into j plus az divided by a magnitude into k. So this is the unit vector in terms of ax, ay and az magnitude and the vector a magnitude. So now different scenarios come in engineering statics. Sometimes we are given the ax, ay and az magnitude. So if we are given ax, ay and az magnitude, we can always find the a magnitude by taking the square root on the sum of ax square plus ay square plus az square, and we find the magnitude, and then we can find this ratio. And in terms of the direction cosine angles alpha, beta and gamma, as we have discussed, that unit vector a is also equal to cos of alpha I cos of beta j plus cos of gamma k. So this is the unit vector in terms of ax magnitude and a magnitude, ay a magnitude, az and a magnitude. So if we compare both of these, then we can say that this ratio is equal to cos of alpha. So we can say that ax divided by a magnitude is equal to cos of alpha, ay divided by a magnitude is equal to cos of beta, and az divided by a is equal to cos of gamma. So now again, if we are given a vector in terms of ax, ay and z, or in other words, if we are given a given vector in terms of Cartesian vector like axi plus ayj plus azk, then, and if we are asked to find the direction cosine angles which are alpha, beta and gamma, so then what we will do is that we will find the vector a magnitude by applying the Pythagoras theorems. And let's say if we are given a vector and which is 2i plus 3j plus 5k, let's say, and we are asked to find angle alpha, beta and gamma. So we can find angle alpha, beta and gamma. What we can do is we can always say that in terms of alpha, beta and gamma, this will be equal to, since this is the ax component, so in terms of alpha, beta and gamma angle, we can always say that this will be a magnitude cos of alpha. As I have told you that these angle alpha, beta and gamma, these are the angles with x, y and z axis, and ax is acting along the x-axis, ay is acting along the y-axis, and az is acting along the z-axis. So if this is the case, then the angles, this alpha, beta and gamma angles are made with ax, ay and z-axis respectively. Then ax will be the cos component, ay will be the cos component, and az will be the cos component in terms of alpha, beta and gamma. So we can say that this 2 will be equal to a cos of alpha, this 3, which is the y component of this a, will be a cos of beta, and this 5, which is the component, which is the z component of this a vector, will be a cos of gamma. So we can say that this a cos of alpha is equal to 2. We can say that ay is equal to a cos of beta equal to 3. And we can say that az is equal to a cos of gamma equal to 5. And now that we want to find angle alpha, beta and gamma, so we can say that a cos of alpha will be equal to 2 divided by a magnitude, cos of beta will always be equal to 3 divided by a magnitude, and cos of gamma is equal to 5 divided by a. And now we only need to find a magnitude using this vector. So we can find a magnitude. We can say that a magnitude is equal to 2 square plus 3 square plus 5 square under the square root. So this will give us a magnitude. So this is 2 square plus 3 square plus 5 square. This gives me 6.16. So this magnitude is equal to 6.16, right? So plugging this in value here, so this will be 2 divided by 6.16. This will be 3 divided by 6.16, and this will be 5 divided by 6.16. And taking the cos inverse will give you angle alpha, beta and gamma. So now we can say that angle alpha will be equal to cos inverse of 2 divided by 6.16. So this is equal to, we can say, 71.05 degrees. Similarly, if we take cos inverse for this equation, then beta will be equal to cos inverse of 3 divided by 6.16. So cos inverse of 3 divided by 6.16 is 60 0.86 approximately degrees. And similarly, gamma will be equal to cos inverse 5 divided by 6.16. So cos inverse of 5 divided by 6.16 is 35.73 degrees. So this is how, if you are given the Cartesian vector and if you are given the magnitudes of ax, ay and az, the first step will be to find a magnitude using the Pythagoras theorem. And then you guys must always remember that in terms of alpha, beta and gamma, which are the direction cosine angles, ax, ay and az are the cos components. So just close your eyes, write ax, ay and az as the cos components of alpha, beta and gamma, and then equate those components to these magnitudes 2, 3 and 5, and you guys will be able to find angle alpha, beta and gamma.